Great. Good morning, everybody. Make a start now. I'm just going to turn my video off to save some bandwidth while I'm talking. So my name's Mark Bull. I'm going to be doing the OpenMP performance talk this morning, and then I'll be handing back to Adrian to finish off talking about vectorization and so forth this afternoon. So although this is primarily talking about OpenMP, a lot of the concepts here also apply to other multi-threaded programming models that you might come across for programming single nodes. So things like POSIX threads or C++ threads, for example. So obviously the specifics of the syntax are different for those APIs, but a lot of the concepts that I'm going to talk about still apply. Okay, so please feel free to type questions in the chat window as we go along. I'll keep an eye on that and do my best to answer them as we go along. And then I'll also give you opportunity to ask questions at various points as well. Okay, good. So let's start by thinking about how we feel about OpenMP programs. Okay, so OpenMP is a nice interface in the sense that it's really quite straightforward in many cases to parallelize a code with it. It's a lot less effort than MPI, for example, very typically. But although getting a working program is fairly straightforward, getting good performance is more difficult. So you can often run into this kind of situation. So I wrote my OpenMP program and I checked I gave it the right answers and I ran some timing tests and, well, speed up was a bit disappointing, really. So now what do I do? Okay, so most of us have probably been here, or you will be here if you start doing multi-threaded programming. So the question is, what happens to my performance? Where did it all go? And the way I like to think about it is that your performance disappeared into overheads of some sort. And the way I like to think about this is to classify these overheads into different types. So I talk about the 6.5 evils. So what that means, there's really 6 main categories of overhead that you're likely to come across in OpenMP or multi-threaded programs in general. So these are sequential code, idle threads, synchronization, scheduling, communication, and hardware resource contention. And the half is another minor one, which I'll mention very briefly at the end, which is compiler non-optimization. So what I'm going to do is take a look at each of those and discuss ways of tactics for avoiding them as we go along. The first one is really very straightforward, is sequential code. So in OpenMP, all the code that's outside of parallel regions or inside master or single directives is sequential code where only one thread is executing. And the time spent in the sequential code is going to limit your performance. That's just a simple Amdahl's law argument. So for example, if 20% of the original execution time of my sequential code is not parallelized, then I can never get more than 5 times speed up for my code, because that 20% is never going to go away. In that case, the solution is, well, maybe difficult to solve, but it's conceptually straightforward. Your problem is that you still have too much sequential code in your application, and you need to find ways of parallelizing the stuff that you haven't already parallelized. Very straightforward idea. The next one is idle threads. So what can happen here is that some threads finish a piece of computation before others and have to wait for others to catch up. So this is typically what we talk about as being load imbalance. So for example, OpenMP is full of implicit barriers. Okay, so every time, the end of every parallel region in OpenMP, the end of every parallel loop, there's an implicit barrier. So all the threads synchronize at that point. And very typically what can happen is that, so if I imagine that I've got an activity diagram like this, so where time goes from left to right, and each bar represents the activity on one of the threads. We've got 4 threads here, and the blue bit is where the thread is doing some useful work, and the red bit is where it's finished and is waiting for other threads. So for example, the 3rd thread here takes longer than the others, all the other threads will be sitting idle in the barrier at the end of the parallel loop or the end of the parallel region, waiting for the 3rd thread to finish. So that's a very, very classical load imbalance problem. So what can you do about it? Well, if it's a parallel loop, then we can experiment with different schedule kinds in OpenMP. So you've got static, dynamic, guided, auto, and you can choose the chunk size for the static and dynamic schedules, for example. So there's quite a lot of experimenting you can do to find a good schedule for your loop. There's a useful convenience there is you can use schedule runtime to avoid recompiling while you're doing that experimenting. So what that does is it allows you to pick up the schedule clause from an environment variable. So it means you can run with lots of different schedule options. You can do multiple runs with lots of different schedule options just by changing environment variable and not having to recompile your code. If we have very irregular computations, then using tasks can be helpful, because the runtime is then supposed to take care of the load balancing for you. And so using OpenMP tasks is basically saying, okay, here's a bunch of independent computations, and the runtime is supposed to schedule them as best as it can for you and take care of the load balancing. Tasks can be useful in the situations where you might have sort of nested parallelism, but all your levels of parallelism have bad balance. So that can be difficult to solve with loops and loop scheduling, and so it can be useful to use tasks in that kind of situation. Just as an aside, it's not always necessarily a safe assumption that just because 2 threads are doing the same number of computations, then they're actually going to take the same time to execute. And the reason for that is that if the time taken to load and store data might be different, because it might depend on if or where that data is cached. So just because by inspecting the code, you can see that, that all your threads appear to be executing the same number of loop iterations, and each loop iteration has the same statements in it, that doesn't necessarily guarantee you that all the threads are going to take the same amount of time to execute it, because what you don't see is in the code is necessarily the cost of the data accesses that are happening. There's other possible situations where threads can be idle. So in particular, synchronization like critical sections. So threads can be idle there. So there's an OpenMP that can be critical regions with a critical directive, or atomics, or lock routines, for example. So again, here's my activity diagram, and suppose that there is a section of code, which is the green stripy thing here, which is a critical section which only one thread at a time is allowed to execute. So what might happen is that the first thread reaches that critical section first, it goes ahead and executes it, but the other threads have to wait their turn to get access to the critical section. So that might mean that they have to wait. So they have some idle time here while they're waiting to enter the critical section. What can you do in this kind of situation? Well, obviously you can try to minimize the time spent in the critical section. So it can be very important to work hard to do essentially sequential optimizations on that critical block of code, on the block of code that's inside the critical section, so that that runs as quickly as possible and minimizes the time that other threads have to wait. In OpenMP, critical regions effectively use a global lock. But if you're trying to protect different shared variables, for example, in different parts of the code that don't need mutual protection, you can use critical directives with different names. Not a very common use case. Much better is to try and use atomics, if at all possible. And so that allows a lot more optimization. In particular, if you use atomics, and that permits concurrent updates to different array elements. So if the thing that you're trying to update is an array element, if you use a critical region, then that blocks access to the entire array. Whereas if you use atomics, then, well, it's not absolutely guaranteed, but most implementations will permit concurrent updates to different array elements. And there are also, you can go beyond the simple atomic update. There are other atomic forms in OpenMP these days which can be useful. You can do atomic writes, atomic reads, and atomic captures. And so a capture is where you can update a shared variable, but you can also, at the same time, as part of the same atomic operation, either store the old value or the new value in a private variable as part of the atomic operation. So that actually allows you to do more things with atomic than just do an update. And your final option is to use locks. So you can, if atomics are not applicable because it's not just a simple update, or the thing you're updating is not a basic type, then you might need to resort to using locks. So you can declare your own locks in OpenMP, and you can, so that gives you all the flexibility that you could possibly want to associate different locks with different parts of your data structures, and so that you're only locking where you need to, and you're not mutually excluding threads from updating different parts of shared memory. Okay, good. Any questions so far? Okay. So my next evil is synchronization. Every time we synchronize threads, there is some overhead incurred, even if the threads are never idle. So even if all the threads reach the end of a parallel loop or end of a parallel region at exactly the same time, then there is still some cost associated with actually synchronizing the threads. Because it means that the thread is because the threads have to communicate somehow, right? And all the synchronization is really done through the memory system, so it's there is some cost associated with that. And perhaps one of the downsides of OpenMP is that it encourages you to write code that's full of implicit barriers. Because every time you enter parallel region or enter parallel loop, there's a barrier synchronization which synchronizes all the threads. And barriers can be really quite expensive. So it depends obviously on the number of threads, but also on the runtime, so the implementation, which compiler you're using, and also the hardware you're running on. But as a typical number, it's thousands to tens of thousands of clock cycles to synchronize threads. So that's if your parallelism is fairly fine-grained, if there's not much computation inside a parallel loop, then you can very easily run into a situation where the overhead of the barrier synchronization completely dominates. And the other forms of synchronization, criticals, atomics, locks, they're not free either. So again, even if threads don't have to wait to enter a critical region, just the act of acquiring the global lock and releasing it again has some overhead associated with it. And then also, if you're using tasks, creating and executing tasks comes with some significant overheads as well. How do you avoid this? Well, one thing to think about is trying to parallelize at the outermost level possible so that you minimize the frequency of barriers. So this is thinking about parallelizing outer loops rather than inner loops. That might not be easy. That might require you to reorder some loops in your code. And then that might in turn lead on to you having to reorder array indices as well to keep your loops cache friendly. But generally speaking, it's often easiest. The first thing you think about is, okay, let's look at the innermost loops are often simple to analyze, simple to parallelize, but they might, you might just drown in synchronization overheads by going down that route. And if that's the case, then you have to rethink and say, okay, I need to exploit coarser-grained parallelism somehow. So either that's different parallelism, or it's transforming the code so that you have more work inside a parallel loop. There is a mechanism in OpenMP to suppress the barrier at the end of a parallel loop with the no wait clause. So that's another possible tactic, but you do have to be very careful with it. It's very easy to introduce race conditions by removing barriers that are required for correctness. And the more loops that you have in a parallel region, the harder it gets to reason about where you need barriers and where you don't. And finally, so just going back to atomics again, they're not guaranteed by the specification to have less overhead, but typically they do. So it's although it's a quality of implementation problem, and then generally speaking, using atomics where possible is a good idea. So the next possible problem is scheduling. So if we create computational tasks and then we're relying on the runtime to do the assignment of those to threads in some way, then we're going to incur some overheads. So the runtime takes some time to do that. Some of that may actually be synchronization costs. It might be internal synchronization in the runtime. So the examples where this happens, if you have so non-static loop schedules, so dynamic or guided loop schedules, and task constructs. So if I do something like this, so if I have a parallel loop with a lot of iterations and maybe not very much work, maybe one or two simple statements inside the loop, then if I choose a chunk size of 1, so that means that every thread just does one iteration and then waits for the next one to come free, or executes the next one that hasn't been started yet, then that might not work out well. So you might just end up with very high scheduling overheads. So the message here is really that you need, in this kind of situation, if you're using dynamic schedules or tasks in particular, then it's important to get the granularity of those tasks right. If you have too few big tasks, then you probably will end up with idle threads because the runtime won't be able to successfully balance the load for you. But if your tasks are too small, each one executes too quickly, then you can just end up with lots of scheduling overheads instead. So it's often a case with dynamic parallelism like this that you need to think quite carefully about the granularity. And it often actually pays to build that into your code. So it pays you to have to build yourself a mechanism for easily adjusting the granularity, so that you can give yourself a tuning handle to play with in that case. Okay, any questions about any of that? Okay, so far so good. Now on to the more difficult stuff. So this one is particularly tricky. So communication. Why is it hard? Well, because when we're on a shared memory system, communication is disguised in some sense. Okay, it appears in your program as increased memory access costs. That's because it takes longer to access data in main memory or in another processor's cache than it does to get it from the local cache. And as Adrian talked about yesterday, memory accesses are expensive. It's order of 100 cycles for a main memory access. Even bigger than 100. It's for the AMD Rome chips. It's 200 odd cycles for a main memory access. Compared to maybe 3 cycles for a floating point operation, and depending on the cache level, it's 1 or 2 cycles from level 1 cache, maybe order of 10 cycles from level 2. And communication between processes is taking place via the cache coherency mechanism that Adrian talked a little bit about yesterday. There's a big difference between shared memory and message passing, because in message passing, it's very easy to look at your program and see where the communication is happening. The only place that communication can happen is when you call the MPI library. So, obviously there's some subtleties there. You don't know exactly when things are going to happen, but you can at least look at your, you don't know exactly when data is going to be sent, but you can at least look at your program and easily understand where communication is happening, because it's all inside the MPI library somewhere. Shared memory is different because your communication is fine-grained. It's on the level of individual loads and stores, and it may be spread throughout the program in a way that's not obvious. You can't just easily look at an OpenMP program and immediately say, okay, that load of that variable there is going to be a coherency cache miss because it's just been written by some other thread. So that kind of just eyeballing programs doesn't work in this case. The other problem that this fine-graininess causes is that it's much harder for tools to monitor it for you. So it's reasonably straightforward for a performance analysis tool to intercept MPI messages and record everything that happened. Okay, so when it was sent, when it was received, how much data you sent. So instrumenting message passing programs is relatively straightforward. Doing the same thing with shared memory is much more difficult, because everything is happening at the level of memory accesses. So instrumenting every single memory access is very difficult and expensive to do, and typically will slow your program down by orders of magnitude if you try to do that kind of thing. It's not impossible. You can do something. It can be done, but it's much more difficult and expensive process for tools to do. Okay, so again, just a brief description of what's going on with cache coherency. So this is the process by which the hardware ensures that even though there might be multiple copies of a data item in the hardware in different caches attached to different cores, then there is still a well-defined value at any one time. So if two concurrent reads happen to that data item, you are guaranteed to return the same value. So a very brief description of how this works is that whenever a thread writes a data item, what it gets is an exclusive copy of that data in its local cache. So it becomes the owner of the only valid copy of that piece of data. And any copies of that data in other caches get invalidated. So when the write happens, all the other copies in the system get invalidated to make sure that other cores, other threads can't read the out-of-date values. So then subsequent accesses to that data item by other threads have to get the data from the exclusive copy somehow. Okay, and that takes time because it requires essentially requires moving data from one cache to another. And cache-to-cache transfers are also expensive. So you say again, it depends on the hardware, but very roughly speaking, the cost of moving data between caches is roughly the same as accessing the cache or memory at the next level down. So for example, if I have level 3 caches to transfer data from one level 3 cache to another level 3 cache, the cost of doing that is very similar to fetching data from main memory into the level 3 cache. So cache-to-cache transfers are expensive. Okay, so I realize that cache coherency is actually if you go into the details, it's really complicated how it actually works. So this is a very simplified description, but it's sufficient for us to reason about the behavior of multi-threaded programs. So this idea that every time a shared variable is written, then the writing thread gets this exclusive copy in its local cache, and then any subsequent accesses to that thing by other threads will be more expensive because of that. Okay, so that leads us to thinking about issues of data affinity. So just the way caches work is that data will be cached on the processes which are accessing it. So we need to reuse cache data as much as possible. So this is really an extension of the ideas with sequential optimization. So we need to write code with good data affinity. So we want to ensure that the same thread accesses the same subset of program data as much as possible. And it helps to try to make these subsets reasonably large, contiguous chunks of data for reasons that I'll come on to in a minute. It's also important to prevent threads migrating between cores while the code is running. So in general, you can do this with an OpenMP environment variable. You can set OMP proc bind equals true. On systems like ARCHER2, you don't need to do that. That's the binding is taken care of you by Slurm. So that's all done for you. So as long as you use the appropriate Slurm options, so use the suggested srun parameters and options in your batch script that we provide for OpenMP or mixed MPI OpenMP programs, then the batch system takes care of the binding of threads to cores for you. Okay, so here's an example. So here I've got, I have two doubly nested loops here. And the important thing to notice here is that both these loops access this two-dimensional array A here. And so A gets written in the first loop nest and read in the second loop nest. Okay. So I want to focus on this second loop nest first, because it has the property that the load on the parallel loop here. So here's my OpenMP directive, which parallelizes the I loop across threads. So different threads will get different values of I to execute. It's badly balanced because the length of the J loop depends on I. So this is one of these triangular loop nests. So because the I loop is badly balanced, then you might, to avoid low balance overheads, you might use for example, you might say that, okay, I want to use a static schedule with some chunk size. So you maybe do some experiments to figure out a sensible chunk size for this particular loop. But then when we go look at the first loop, this one's balanced because J runs all the way up to N here. But that gives us a problem because of the interaction between these two loops. The access pattern, so typically the thread which is reading a particular value of Aij in this loop, because of the different schedule, is not the same thread that wrote the value here. So most of these, so provided A is small enough to fit in some level of cache, then all of these accesses, or most of these accesses here, will result in cache misses, because the writing thread up here is different from the reading thread down here. So this particular case is quite easy to fix. You could simply apply the same schedule, the same static 16 schedule to the first loop. That shouldn't introduce too much in the way of additional overhead for this loop, but it then will ensure that the same thread is accessing the same data in both loops. So another example here. So this is where I have a parallel loop that reads. So the ith iteration reads the ith element of an array A. And then I have a sequential loop. So this one is not parallelized. That sets the values, that writes values into A. And then we have another parallel loop, or the same, it could be just the same one again, which reads A. And your initial thinking may be that, well, you've done some profiling, and it doesn't look like this loop is particularly worthwhile parallelizing. There might be lots of other code in these loops here. That means that these loops look like they're worth parallelizing, but this one doesn't. or maybe you just didn't get around to it yet, or maybe it's in, it's in a different, it happens to be in a different routine somewhere. So it wasn't obvious that you needed to take care of this one. So again, what happens here? Let's think about where A is being stored. Okay, so every thread that reads a value of AI will typically store that value in its local cache. But then when the single thread writes these values, all those other copies get invalidated. And this thread here then owns all the exclusive copies of A in its local cache. And then when we come to do this loop again, all these accesses, well, all the ones apart from on thread 0, will result in cache misses again. So again, we have a problem where the cache coherency mechanism is implying lots of data movement between caches, and which can be bad. So one thing you will notice if you do careful profiling here is that this sequential loop, so this loop in the middle here, which is being executed by one thread, this can actually take longer as you increase the number of threads. So if you go from one thread to 2 threads to 4 threads executing the parallel loops, what you will see is a maybe slightly unexpected effect, is that this sequential loop will actually start to take longer. And the reason for that is that it is to do with the invalidations that have to happen. Okay, so getting the exclusive copy and invalidating other copies in other caches is not free. So you can see that effect happening sometimes. And what you'll also see is that the second parallel loop will scale badly because of the additional cache misses that are going on. Okay, so this can mean that to ensure good data affinity, you might need to end up parallelizing code which doesn't appear to take very much time in your sequential program. So when you profile your sequential program, you might think that that's not really my first priority for parallelizing that little loop, but it can have consequences for communication. So in this case, again, solutions are fairly straightforward. You could either just straightforwardly parallelize this loop. So more of a problem might be if this loop is not parallelizable. Okay, then you might have a real headache to think about. So suppose that this could be an inherently sequential loop, for example, where AI depended on AI -1, and then you'd have to really potentially rethink how you were doing your computations. But in this case, you could either just parallelize this loop, or even better probably would be to merge this loop with either the one before or the one after, if that made sense in the context of your code. Okay, so that's really communication due to cache coherency. There are other problems which we can come across. So the next one is NUMA effects. So this is still effectively it's still a communication problem. So this is very evil. And the problem here is that on multi-socket systems, the location of data in main memory is important. Okay? And so, all current multi-socket, so x86 type systems are NUMA. So most current supercomputers have 2 sockets in a node. Things are getting worse, okay? So with the new AMD Rome processors in ARCHER2, not only do you have 2 sockets in a node, you also have multiple NUMA regions in a single socket. So we actually have 8 NUMA regions in a node. So each 64-core chip has 4 NUMA regions. So each set of 16 cores has its own local piece of main memory. So this kind of system, which is becoming really prevalent, and it matters where data in main memory is located. And OpenMP doesn't have any direct support for controlling this. So there's nothing you can do in your OpenMP program directly to influence where your data is located in main memory. The common default policy is for the operating system to place data on the processor. So by processor, I mean the NUMA region. So that's attached to the core which first accesses it. Okay. So whichever core is the first one to read or write that data item, then the operating system will place the data in the piece of main memory that's attached to that core. So this is a so-called first touch policy. And basically that's the default policy in Linux. So it's pretty ubiquitous. And you can understand that. So for sequential applications, that makes sense. Okay? The application is running on this core, put its data in the nearest memory. It also makes perfect sense for MPI programs. This MPI process is running on this core, so put the data for this MPI process on the attached memory, in the attached memory. Unfortunately for OpenMP programs, it can be the worst possible option. The reason for that is that if your data is initialized outside of any parallel region, so if your data is initialized in the master thread, then the first touch policy will mean that it's all allocated into one socket or one NUMA region. And then the problem is that having all your threads accessing data in the same socket or same NUMA region becomes a bottleneck. You're effectively crippling yourself by reducing the available memory bandwidth down by a factor of however many NUMA regions you have in the node. In practice, with hybrid MPI OpenMP programs, what this often means is that, in fact, it rarely makes much sense to run threads belonging to one MPI process across multiple NUMA regions. So for a system like ARCHER2, then it's you're almost certainly going to want to run at least 8 MPI processes per node, so that each MPI process can be run on a different NUMA region, and all the threads associated with a given MPI process will run in the same NUMA region, so that you don't have multiple threads associated with the same process running across different NUMA regions. Okay? There may be exceptions to that, and you may be forced into fewer MPI processes than that for memory reasons, but for performance reasons, that's probably going to be the case. In general, though, what can we do about this? Well, you can try to persuade. One thing you can power to persuade is to persuade the operating system to do something different, okay, to change its default policy. So for example, in Linux, you can use the NUMA command, which basically takes your executable as an argument to change the policy, for example, to round robin. So it'll just spread your pages of data in a round robin fashion across all the NUMA regions. The other thing you can do is to try to take advantage of the first touch policy. So you can use that to control the data placement indirectly by parallelizing your data initialization. Okay? So that might seem completely not worthwhile in view of the insignificant time it takes in your sequential code. So you might be, your data initialization might take half a second, and you're going to run your code for 12 hours. So why would you bother parallelizing the data initialization? Well, that can be really important to make sure that your data does in fact get spread out across different NUMA regions. Typically, you shouldn't worry too much about getting the data distribution exactly right. So exactly how you parallelize your data initialization might not matter too much. The important thing is to make sure that you get the distribution. So, distributing your data across NUMA regions is much better than having it all on one NUMA region. Exactly how it's distributed might not matter quite so much. Now, this might be easy or difficult depending on the nature of data structures in your code. If your main data structures are large multi-dimensional arrays, then parallelizing the initialization is typically pretty straightforward. Okay, you just need a nested loop to set all your array to 0. You can easily parallelize that with OpenMP. If you have more complicated data structures, then it gets much messier. So if you're building dynamic graphs or trees or something like that as your main data structures, then parallelizing your initialization may be a lot more difficult and complicated to do. If you're thinking about doing this, then you just have to remember that the allocation of data to NUMA regions is being done at the operating system page level. So that's a reasonably large granularity. So that's typically order of kilobytes. Okay. And might be a reason why you didn't want to use large pages. And yet another communication issue is good question. So any API can be used inside the program to be used to determine on which NUMA node the given memory address resides. I'm fairly sure the answer is yes. You can. There are Linux system calls which can tell you that, but I would need to go and look them up to tell you what it is. Yeah. Yep, tools like Liquid might help with you that as well. Yeah. So does where you perform memory allocation matter? So it's actually not the allocation that matters here. It's the initialization. It's the first access. So typically, if you just doing the memory allocation does not cause the memory to be actually placed by the operating system. It only happens when you first read or write that data. Okay, yeah, false sharing. So this is again, this is a nasty side effect of the cache coherency mechanism. Okay. So you think of this process by which caches get exclusive copies of data items and invalidate other copies. The units of data on which those operations are happening are cache blocks or cache lines. Okay? So those are typically of the order of 64 or 128 bytes long. But the important thing is that they're always bigger than a word. Okay? So the problem that can happen here is that if you have different threads writing to neighboring words in memory, that can still cause cache invalidations to happen. Okay? So you're not logically sharing any values between threads. You just happen to have threads which are reading and writing data which reside in the same cache block. And it's still a problem if one thread is writing and others reading. It's okay. If all threads are reading, then that's not a problem. Every thread just gets its own copy in its own local cache and keeps reading it. But as long as at least one thread is writing, then you will cause the invalidation process to happen. So that's nasty because it's very difficult to detect. So you really just have to think, just have to have it in mind when you're writing code. Usually the worst cases occurs are when different threads repeatedly writing neighboring array elements. So you might have a pattern like this. So you might want to say, okay, I want to count some event that's happening on every thread. So I have a shared array, and I use my OpenMP thread number as an index into that array. And every time something happens, I'll increment that element of the array. So that kind of pattern can cause false sharing because you have neighboring threads writing neighboring addresses in memory, which are going to be stored in the same cache block. You can also run into it with code like this. Okay, so suppose to one of my triangular loops again. This time focuses on the array that's being written to here. So if for example, if I use a schedule here with a chunk size of 1, what that means is that so thread 0 will execute I equals 0, thread 1 will execute I equals 1, and so on. So I get a cyclic distribution of I values across the threads. Then again, that means that different threads are writing neighboring memory locations in this array B here. And so that can cause a problem. What you'd see in practice in this case would be that you just might, if you experiment with changing the chunk size here, that 1 is not optimal, that you need to use a larger chunk size to avoid this problem. Okay, any questions about that? Okay, last of my 6 is hardware resource contention. So you find that the design of shared memory hardware is, there's cost versus performance trade-offs going on in here. And there are shared resources which, if all your cores try to access them at the same time, don't scale. So you can think of it the other way around, though. You can think of it as say, okay, an application that's running on a single core can access more than its fair share of the resources. So you can take a glass half full or glass half empty view on this. But nevertheless, it means that if you do scaling experiments, you can see poor scaling from 1 to 2 to 4 to whatever number of threads, because they are not getting because they are sharing resources. Okay, so the question is there any tool that set the correct chunk size by running the algorithm problem? No, not really. I mean, the choice of chunk size is very situation dependent. Okay, because it depends on it depends on the way it depends on the load balance. It depends on the way that the loop accesses memory, on the memory access pattern in the loop. So choosing the right chunk size is incredibly difficult, and it's very situation specific. So there's nothing very much you can do apart from running experiments. One tip that I do sometimes recommend, though, is that instead of tuning the chunk size directly, so the problem here is that the optimal chunk size often depends on the number of threads. So it's actually better in some cases not to tune the chunk size directly, but what you actually tune is the number of chunks per thread, and then derive the chunk size from that. So you can have the expression in the schedule clause for the chunk size in OpenMP doesn't have to be a compile time constant. It can be a variable expression. So that's potentially more robust strategy, is to tune the number of chunks that each thread is going to execute rather than the chunk size directly. So what metrics should you look for if you suspect that cache coherence is the limiting factor? Increasing cache misses. Yes, absolutely. Yeah. So if you see increase in numbers of cache misses, so particularly in so it'll be could be either level 2 or level 3 cache misses in current architectures that you're looking for typically. Problem is that it is, yeah. So particularly on, so yeah, shared if. Let me say, okay, depends on the architecture. If I have a shared cache across all the cores in my chip, so that's typical Intel designs, then you're only going to get cache misses if you've got threads running on different sockets. You're only going to get coherency, L3 coherency misses if you've got threads running across different sockets. The AMD ROMs are different, though, because the L3 is only shared between groups of 4 cores. So as soon as you are running more than 4 threads, then you can potentially have cache coherency between different L3s. And then even if you're running in the same, even if your threads are running using the same L3 cache, you can still get cache coherency misses between the L2s, because every core has its own L2 cache. So those also need to be kept coherent as well. But typically the cost of an L2 miss is less than the cost of an L3 miss. And what your cache miss statistics do not tell you is whether this is genuine communication or fault sharing. Okay, so your hardware counters will not distinguish those two cases for you, which is a pain. Okay, so yeah, resource contention. So particularly cores can contend for memory bandwidth. They can contend for cache capacity in shared caches, and they can also contend for functional units if we're using simultaneous multi-threading. The most important one is probably memory bandwidth, because codes which are very memory bandwidth hungry and just do not scale linearly on almost any shared memory hardware. And you can try to reduce your bandwidth demands, obviously, by improving locality and reuse, improving the reuse of data in your caches. That's going to benefit the sequential performance as well. So really, it's the same optimizations you'd be looking at to improve cache reuse and reduce memory bandwidth demands. Okay, so it's a little, try not to fill these talks with too much data, but I think this is an interesting example. Okay, so this little experiment I ran on ARCHER2 on the AMD ROM. And I restricted myself just to running inside one NUMA region. Okay, so just up to the 16 cores that are attached to the same piece of main memory. So there's no NUMA effects going on here. Okay. So we have each core has its own L1 and L2 caches, and then there's this 16 megabytes of shared L3 cache for every 4 cores. So what I did was just measure the performance of this little OpenMP program. So this is basically just a parallel loop. In fact, it's doing a reduction, doesn't really matter. All that matters really is that it's reading values from an array here. Okay? And I just repeat the execution often enough so that if this array fits in the cache, then it runs often enough so that almost all my accesses will come from the cache. So basically, just ignore the first time, run enough time so that the first time through doesn't matter. And then essentially what I did was vary the value of n, which is implicitly the size, also implicitly the size of the array, and measured the speed up that I get for different numbers of threads compared to the equivalent sequential code without the OpenMP directive. So these are the results. So let me explain what I'm showing here. Okay, so the x-axis here has the number of loop iterations. The y-axis is the speed up, and then the different lines correspond to different numbers of threads. So first thing to note is, okay, actually nothing to do with memory bandwidth. It's just to illustrate one of the other evils, which is the synchronization. Okay? So for small values of n, I get speed ups which are much, much less than 1. And that's basically death by synchronization. It's the overhead of the parallel region is much bigger than the cost of actually executing the loop. So for small values of n, I actually get significant slowdown for that loop. And depending on the number of threads, you need tens of thousands or even hundreds of thousands of loop iterations to get to the break-even point, where the advantages of parallelizing the work outweigh the overheads of synchronizing the threads. Okay, so that's what's going on down at the left-hand side here. Once we get beyond that, then you can see that for 2 threads, that's the blue line here, then I reach, after a certain point, I reach a speed up of 2. Okay? And that persists for all the way out to very large iteration numbers, very large arrays. For 4 threads, I do just about reach 4 times speed up, but then it drops to around about 3 here. So what's happening here is that the way that I arrange my threads here is that all 4 threads are using the same level 3 cache. So what's happening here is actually these 4 threads are contending for the level 3 bandwidth. So you get a lot of bandwidth out of level 3, much more than you do out of main memory, but nevertheless, it's still possible to saturate it with all 4 threads, all 4 cores accessing L3, hammering your L3 cache. And then at some point, the array doesn't fit into L3 cache, and my speed up drops back down to barely more than 2. If I go to 8 threads, then I see some similar effects with some strange wobbles, but then I get a sudden massive increase in speed up here. And that's because I have the extra L3 capacity. So compared with 1 thread, I have double the L3 capacity. So there's a particular range here where my data fits into 2 L3 caches, but not into 1 L3 cache. And I get a massive boost in performance from that. But that doesn't persist. As soon as I go outside the capacity of those 2 L3 caches, then I'm back down again to not much more than 2. Okay. Same happens for 16 threads. Get this boost from having, I get a wider boost here because I've got 4 times as much L3 cache. But you can see once you get outside the L3 cache capacity, then the speed up that you get is, how do you say threads get a speed up? Okay, this is because of the additional cache capacity. Okay, you think about what's happening at this particular size, this particular data size. If I run on 1 thread, then the data doesn't fit in that 1 L3 cache. So all the accesses are coming from main memory. If I split the same computation across 8 threads, then I get to use 2 L3 caches, And if my data fits in, if half the data fits in each of those L3 caches, then all my accesses are coming from L3, which are much faster than from main memory. So you can get these superlinear speed up effects by increasing the number of threads, you're increasing the amount of cache memory that's available. But you can see that once we're out in main memory here, then the speed ups are awful. So I barely get, don't even get. I get about 2.5 times speed up on 16 threads because of the memory bandwidth contention. And so again, you're not quite sure what the effect is here. Whether that you can argue it the other way around. You can argue it that that one thread is actually getting one thread doesn't get a 16th of that memory bandwidth. It gets one thread gets almost can get almost half the available memory bandwidth. So that just means if you do this kind of scaling experiment, what you can see is with very memory bandwidth hungry threads. Can I explain the minimum in the middle? Oh dear, I knew somebody was going to ask that. Okay, so this is where you're between running out of L2 and having extra L3, I think. Okay. So at this point here, for example, on the purple line, this is where I'm dropping out of L2 into L3. So I'm now contending for L3 bandwidth. But then as I carry on further, then I get, because I'm on 8 or 16 threads, then I get the boost from having the extra L3 capacity. There also might be effects here from the fact that the L3 cache is actually banked up into sets of 4 megabytes. So although you've got it's a 16 megabyte cache, it's actually running in it's actually divided up into blocks of 4 megabytes, 4 blocks of 4 megabytes. And exactly the way that your data gets mapped into those blocks can have some performance effect as well. So I'm going to wave my hands a little bit and say it could be down to those kind of effects as to whether you're using all the same 4 megabyte block or whether you have to go across multiple 4 megabyte blocks in the L3. Can you measure bandwidth? Now that is a good question. I have not tried, and maybe Adrian can chip in here and see if he's tried it. I have not tried to see what metrics CrayPat will give me for memory bandwidth on this system. On Archer with Intel chips, it was actually difficult. And it's also complicated by prefetching as well. So Federico asked, is the L3 cache a victim cache? Yes, I believe it is a victim cache. Yeah, so what that means is that whenever you get a new cache block into L3, then the block that it replaces gets stored temporarily, okay? So that if you access the old block again very soon, you don't get a cache miss. Have I tried running 4 threads with 2 cores per L3 region? No, I haven't. Okay. Yeah, there's lots of possible with this kind of architecture. There's lots of possible combinations you can try. That would certainly show you something different. So if you spread your 4 threads across 2 L3s, then you'll see the benefit of having the extra L3 cache capacity. It's just not very realistic that you would probably ever use your system like that. Okay? It's very unlikely that you would leave cores idle in that way. But yes, you can play these games. You say, okay, yeah, I can get much more memory bandwidth if I spread my threads across, across different L3s and across different NUMA regions. But that's, yeah, in some sense, that's just a bit of a curiosity, because you're never really going to run in that. You're probably never really going to run in that mode by leaving lots of cores idle. There are corner cases where you might do that, but it's pretty unusual. Okay, so that brings us nicely on to cache space contention. And so, see where cores are sharing some level of cache. Your codes might not appear to scale well because a single core can access the whole of the shared cache. One consequence of that is if you're tuning block sizes, if you're doing aggressive tuning for cache blocking, then you have to be careful if you're tuning, if you do your tuning on a single thread, but then what you're actually running is multi-threaded code, because a single thread will try. If you do that, then each thread's going to try to utilize the whole cache, and you're going to run out of cache capacity. So you just have to think about your end use case if you're doing aggressive cache blocking optimizations. Hardware threads. Okay, so if we use hardware threads, then OpenMP, so you're then going to end up with multiple OpenM3 threads running on the same core. So they will contend for the functional units, so for example, the floating point units, as well as for the cache space and memory bandwidth. So if this tends to benefit codes where threads are idle because they're waiting on memory references. So codes with non-contiguous or not really random, but unstructured memory access patterns. So codes which are essentially sensitive to memory latency rather than memory bandwidth. Then you can see some benefit from running multiple threads on the same core, because while one of those threads is stalled, waiting for a memory reference, then the other thread can carry on usefully executing instructions. And in practice, codes which are bandwidth hungry or which saturate the floating point units may actually not benefit from this. You can actually see them running slower. It's fairly unusual in HPC context to see codes that get a big boost from using hardware threads. It does happen, but it's not common. And the other way you can, well, another way that you can contend for resources is by oversubscription. So running more threads than you have hardware execution units, be that cores or hardware threads, is generally a bad idea, because then the operating system has to try and give each thread a fair share of the execution units. by context switching, and the cost of stopping one thread and starting another is big. It's order thousands of clock cycles, and it also ruins your data locality, because a thread that's been accessing some data and has stored it in the local cache, if you suddenly start running another thread on that same core, then it typically wants to access different data. So what's stored in the cache is useless for it. So again, not really a big deal in HPC systems running batch, where you're mapping of, you're very carefully controlling the number of MPI processes and OpenMP threads, and having the batch system schedule them and bind them onto your cores and hardware threads and so on. But in general, oversubscription is a bad idea. You can certainly achieve it by screwing up your slurm options, though. That's easily done. If you play around with the slurm options, you can very easily end up in a situation where you bind all your threads to the same core, and that'll be typically total disaster. Okay, so have we seen on ARCHER2 cases in which it was worth to leave one or few cores free for the operating system? I haven't. The answer is really I don't know. Okay, I don't think we've got enough experience yet to say. Certainly, Cray in the past this has not been necessary, because the kernel that's running on the compute nodes is pretty cut down and doesn't tend to try and do very much while your application code is running. My guess is that that's still true on the new system, but I don't have any good evidence to support that. So perhaps, I don't know if Adrian has any comment to make on that. Okay, so the final one is hopefully one that you'll never see, but just in case, so that you're aware that this can potentially happen, is that you get problems with OpenMP can very occasionally cause problems with compiler optimization. So what happens is that adding the compiler transformations that have to be done to implement the OpenMP directives somehow inhibit the compiler from doing its normal sequential optimizations in some way. And what you can see as the symptoms here is if you run your parallel code on one thread, then it has a longer execution time than the sequential code. So if you compiled your code without OpenMP. So it's pretty rare these days, but just so that you're aware that once in a lifetime this could trip you up. It can be pretty hard to find a workaround because it's hard to work out what's really gone wrong. But sometimes be cured by fairly innocuous looking changes to the code, or things like making some shared data private, or making local copies of variables. So instead of using using something that's passed through as an argument to a routine which the compiler doesn't know very much about, making an explicit local copy, which then and use that inside your parallel loop, then sometimes that can help. But in general, it's quite hard. Most recent one I saw was an odd one in Fortran. So there was a code which did something perfectly legal but slightly odd. So when it was passing passing arrays into subroutines in Fortran, it was actually explicitly passing the first element of the array instead of just the name, which is fine, okay, because it's those things have the same address, so it's perfectly legal Fortran, but for some reason that confused G-Fortran with OpenMP enabled, and it's for the main loops in the program, it basically halved the performance. And just by changing back to the sort of the normal way of passing arrays by just their name, fixed it fine, and it didn't affect other compilers. So just so aware that this might happen. It's pretty unusual, but there is a slight possibility you might come across one of those compiler quirks. Okay, so in general, what to do? In the situation where your code is giving you poor speed up and you don't know why, so what do you do now? Hopefully having listened to me, you won't take number one and blame OpenMP for scaling badly, because in general the implementations are actually pretty good. And most of the problems are either in your code or down to the hardware. What you need to do, I think, here is this is really just an extension of the of the normal process you would go for sequential optimization. Is basically try to classify and localize the sources of overhead. So what type of problem is it? Which one of the 6 evils is, or possibly more than one of the 6 evils is causing the problem, and whereabouts in the code is it happening? So if you can figure that out, then you have a fighting chance of doing something about it. It's often good to try and use tools to help you. Just basic timers are very helpful, but also hardware counters and profiling tools, depending on what's available in your system. And obviously, you try to fix the problems which are responsible for the largest overheads first. And then once you fix one problem, measure again and go around. So in terms of profilers, unfortunately for multi-threaded code, your standard profilers like gprof or what you get provided in your IDE can be pretty confusing, because what they do is typically accumulate the time spent in functions across all the threads. So you're actually losing important information about what's happening on different threads. You can get a lot out of using timers. So I typically recommend that if you're doing OpenMP tuning, that you go and add timers around every parallel region and around the whole code, or at least the piece of code that you're interested in the execution time of. So that at least allows you to do it's just an easy way of doing the localization. You can work out which parallel regions you can compute speed up on a per parallel region basis, and work out which ones are causing you the problem. But again, because of this potential with data accesses don't necessarily assume that the time spent outside of parallel regions is independent of the number of threads. So if you measure the whole code and you measure every parallel region, you can do the subtraction to figure out how long you're spending in sequential code as well. Lots of performance tools do have OpenMP support in them. So in particular for ARCHER2, Cray has some capabilities for dealing with OpenMP overheads. As you'll see, it'll give you a chance to play with that in the practical session. As you'll see, it's okay. It's better than nothing. It tells you some stuff. Doesn't tell you everything. And in particular, the stuff that these tools have real difficulty with is communication overheads. Okay, they're quite good at telling you about load imbalance and sequential code and synchronization overheads. They're typically not very good at diagnosing communication overheads. So again, outside the context of Archer, one tool that is helpful is a thing called Paratools Thread Spotter, which works in a very different way. So it's not a traditional profiling tool. So it's what it does is actually instrument your code and take a statistical sample of the memory accesses and dumps that in a trace, and then does some post-analysis on the trace. So it's able to, by doing that, it's essentially running your trace through a cache simulator. So it has much better capabilities for diagnosing communication problems and things like false sharing, which your standard profiling, your standard tracing or sample-based profiling tools just really struggle with. Okay, any more questions? If not, then I've talked for quite long enough, so we'll take a break now and then have an opportunity to carry on with the practical sessions and yeah, just punt us any questions into the chat and we'll do our best with those. Okay, great. Come back and speak to you later on this morning. Okay, let me consult the timetable. So you can, basically the next session is a practical session. So I overran somewhat. The next session is a practical session. So you can just work on your own. I will be back at about, let's say, I'll make sure I'll say something about it at around 12:15. I'll do a bit of a wrap up on the on the OpenMP profiling. And then we'll be back on track for lunch break at 12:30. Okay, hello folks. So just wanted to show you what you're kind of looking for in the CrayPat output here for the OpenMP profiling, and also to sort of kind of illustrate some of its limitations. So it can be useful, but it can also be somewhat difficult to interpret. So essentially, this is what you get out of pat report. So I did the pat build with the -GOMP flag, and this is a run on 16 threads of the original code. And so what you can see is that in this first table here, you a profile by function. So what it tells you is that essentially this here is, so this is difficult for me to point at successfully, I think. No, maybe you can see my cursor. Okay, so you can see that it groups your functions under user, which is your code. OMP, so that tells you about time spent in the OpenMP runtime library. And then etc. is other stuff. So this is basically other libraries and operating system functionality. So what can we tell from this? So so it tells you that most of the time spent in your code came from function forces and from the parallel loop at line 24. Okay, so no big surprise there. What it does tell you though is that there is quite a lot of load imbalance. So this fourth column here is basically a measure of how imbalanced the threads were in the execution of that loop. So that's one indication that there's at least one problem here, is that there is some load imbalance in this loop. Where it gets a little bit more confusing is if you look under the OpenMP category here. So it reports time in OMP set lock. Now, that's confusing because there is no explicit call to OMP set lock in the code. And so what you have to kind of realize, which is not really well documented everywhere, is that under the hood, the OpenMP implementation is using OMP set lock functionality to implement the critical sections. So this is basically telling you this is overhead in critical sections. That's really not that obvious. Okay. And then you also get a flat profile as well. This one also gives you some other stuff. So it also tells you that there is a fairly small amount of time in it. So it does try to attribute overhead to parallel regions as well. So here you can see that there's a small amount of time attributed to the parallel region in forces at line 20. And also there's a bit in unset lock as well. So that's the other end, that's the end of the critical region. We also see time spent in spin weight here. So spin weight is almost certainly what happens underneath if you try to set a lock or enter the critical region, and you have to wait for threads have to wait for other threads. But again, that's not really terribly obvious. So the Cray profile does tell you something, but it requires a fair bit of interpretation, and it's not really the nicest of tools for diagnosing OpenMP problems. Okay, so if I do go and fix the problems, so I can fix the, show you the resulting code. So I can fix the problems. Okay, so I can fix the load balance by putting a small chunk size in the static schedule. So I picked 8 here, but anything reasonably small probably works fine. And then replacing the critical sections with atomic updates at the bottom here. So this is one of these cases where atomic is much better than critical, because it allows different threads to update different elements of this F array in parallel. So you should see a significant improvement in performance, at least once you get to 8 or 16 threads. You should see that makes a significant improvement. And whoops, the resulting profile looks different. It basically tells you that all my time is now spent in the loop, that the imbalance is much reduced. So the imbalance has gone down from 50% to just over 1%. I still have a bit of time in spin weight, but again, that's less than it was. So it's still reporting some overhead associated with the parallel region, yeah, but it's a lot less than it was. So I hope you can see you can get something out of that, but it's not the most user-friendly or clear interface, I think. I tend to prefer other tools such as Scholastica for diagnosing OpenMP problems. It does a much better job of showing you what's going on and attributing overheads back to actual OpenMP directives rather than to the functions that the OpenMP library, the runtime library, is using to implement the directives. I'm not sure whether we've got that on the system yet. I suspect not, but it's something we should almost certainly look at installing on ARCHER2. Okay, so any questions about that? Okay, so that was the default number of time steps, which I think is 20. It's actually a bit short for sampling, so you could probably, you would probably want to bump up the runtime a bit. It's a rule of thumb. It's always good to have a runtime of more than 10 seconds or so for sample-based profiling. So just let me remind myself what difference that made in terms of performance. So on either. And it eventually. Okay, so the original code takes about runs about 6 seconds on 16 threads, and the optimized version runs at about 1.5, 1.4, 1.5 seconds.